Okay. Hello, good afternoon. I'm very pleased to be with you this afternoon. My name is Mike. I'm now retired, but I worked in the semiconductor industry for over 40 years, mostly as an engineer, often now called a silicon chip engineer. I was involved in the research, development, and manufacture of silicon, gallium arsenide, germanium, and indium phosphide semiconductor products. The first slide actually shows the more recent environment I worked in, which is actually what we call a wafer fab, sited in Groby, just outside Leicester. And you can see that I'm wearing all sorts of funny clothing. This is because a wafer fab nowadays is very much like an operating theatre. It's very clean, but it's not sterile. The environment that I worked in uses very high temperature furnaces, 1,000 degrees, high vacuum equipment, plasma etching equipment, photolithography equipment, and very dangerous chemicals. Also in the area, there's a heavy use of computers, robots, and microscopes, both optical and electronic. What is a semiconductor? Well, a semiconductor is a material which is a good conductor, but not as good as copper. And it's also an insulator, but not as good as glass. What makes it very special is that by adding a dopant, which is sort of an intentional contamination, you can change its properties. So by adding, for example, in silicon boron, you can make it what's called p-type, which is like the positive electrode on a battery. By adding arsenic, you make it n-type, which makes it like the negative contact on the battery. By varying these dopants in different areas of the silicon, we produce things called diodes, and most importantly, something called a transistor, which is the most important electronic component in all of what's called silicon chips. In today's technology, some of the chips may contain billions of transistors. In the picture A, you can see a sandy beach. Silicon, being a very common element on the planet, is found in sand, for example, which is actually silicon dioxide. This material is taken and refined and then melted to produce silicon melt, and then you can draw an ingot. The image in B is a slice through a crystal pulling machine to produce ingots, which are then processed and sliced up into individual wafers, which is shown in the image on the right. On this slide, I've just tried to show you where silicon lies in the periodic table. It's actually number 14, and I'm sure that your teachers can explain a bit more about the periodic table. On this slide, image A is a very simplified flowchart of how you produce a silicon chip from an ingot, slicing it, carrying out various photo processes, chemical etching, high temperature processes, applying metals in high vacuum equipment. In image B, you can see a typical silicon wafer, and the rectangular objects on the wafer are individual chips. After the wafer has been completed in processing, it's sliced up into individual chips, as in image C and D, and then tends to be packaged in packages which can then be inserted into electrical circuits. Image. When I started my career back in 1970, things were very different. I looked very different as well. I have included my security pass from 1975 on the left. And as you can see, I had hair then, which I don't now. The laboratory that we worked in was also very different. we only wore white coats, and the critical work was carried out in glove boxes. During the early part of the semiconductor research and development work in the 70s, most of the end products I worked on ended up in military applications, missiles, radars, in ships, aircraft, helicopters, and a lot of communications devices. The non-military applications were typically communication systems for the BBC, outside broadcast, etc. The military applications were part of what history now calls the Cold War. Latterly, the silicon processing has become extremely complicated, and during the noughties and teens, I was part of a team which did research and development and manufacturing of very advanced semiconductors produced by what's called micromachining. You can see the top three images are SEM images of silicon wafers at various forms of magnification, very complex devices. Most of these devices were designed and produced at Groby, just outside Leicester, and used in applications such as aircraft, Formula One racing cars, and under the sea. During the 80s and 90s, the company I was working for then produced a lot of semiconductors that were used in space applications, mostly satellites, but also one or two deep space missions. And I was fortunate to be involved in the development of these devices and also the manufacture and inspection before they went into the satellites. The two that I'll mention are Giotto and Cassini. In 1986, ESA carried out its first deep space mission, which was called Giotto. Giotto was a spacecraft which rendezvoused with Halley's Comet and sampled the tail of the comet, as well as taking images. A comet is an icy ball of rock which originates out further than Neptune in what's called the Oort cloud and has a very elliptical orbit which brings it close to the sun. When it gets close to the sun, it heats up, the ice melts and produces a gaseous tail, which is what you can see in the images on the lower half of the screen. The mission was very successful, and in fact, the spacecraft was sent on in 1992 to another comet, where it also sent back information. During the 90s, I was involved with the research, development, manufacture of components that went into a very important mission which went to Saturn. This was called the Cassini-Huygens mission. And you can see an image there of the trajectory that the spacecraft took. Now you can particularly see that it was not a direct route. And the reason for this is that as the spacecraft travels, it loses velocity. So the spacecraft trajectory was designed to actually gain trajectory by having close approach to Venus twice, Earth, and also Jupiter. It arrived in the Saturnian system in 2004. I've included here a little bit extra on the trajectory, and on the top right hand, you can see a little diagram which explains why you have these bypasses, as they call, of a number of planets. As a spacecraft approaches a moving planet from the right, as you can see, from behind the planet, it gains a little bit of velocity from the gravity of that planet. If you send the spacecraft in front of the planet in a retrograde fashion, it tends to lose speed. And this is all consistent with Newton's law of gravitation, which I've included down the bottom right for some of the more advanced students. On this slide, you can actually see a graph of how the velocity changed with time. So in the y-axis, you have velocity, and in the x-axis, you have time in the form of the actual dates. and you can see the peaks and troughs. The peaks as the spacecraft approached a planet to do a flyby to gain velocity. This happened, as you can see, 3 times. And then eventually the spacecraft reached Saturn, gained velocity again. And then what looks like noise is the spacecraft actually moving around in the Saturnian system. Cassini spacecraft was a very large spacecraft, about the size of a bus, double-decker bus. The top half was predominantly concerned with communication back to Earth, and most of the instruments for analysis were in the middle, and the rocket motors at the bottom. On the right-hand side was attached the Huygens probe, which was a ESA designed, built, and attached probe to land on one of the moons of Saturn called Titan. Here I've got a number of rather beautiful images of Saturn, which I'm sure your students have probably seen before. Saturn obviously has the rings. The image in the middle is a bit of a cheat because they put a cartoon or a picture of the Cassini spacecraft. But of course, you couldn't take this photo because the spacecraft was taking the photo of Saturn. The one on the right actually shows a small dot, which is Earth seen from the Saturnian system. You can find lots more photos of Saturn on the NASA website. It arrived in 2004, and in January 2005, the Huygens probe landed safely, soft landed, on the surface of Titan, which is the largest moon of the Saturnian system. It came down by parachute because Titan has an atmosphere mainly made up of methane. The spacecraft itself is shown in image B. A and C are animations or drawings of what it would have looked like had you been on the surface of Titan. The images at the bottom actually show the real photos taken by the lander as it was coming down, which is in D, on the surface in E, and from high above on F. Titan actually has an atmosphere which is composed mainly of methane. Methane is in all forms on the surface of Titan. So you have liquid methane, gaseous methane, and solid methane. In fact, we believe that it actually snows methane on Titan. The lander survived, managed to communicate back to the Cassini craft, and the data was transferred to Earth. The lander survived for several hours, which was what was planned, but is still on the surface of Titan now. Whilst in the Saturnian system, the Cassini spacecraft, which was there for 13 years, carried out lots of flybys of all of the moons of Saturn and discovered quite a few more. One in particular, which it was sent to investigate, was Enceladus. And Enceladus was very interesting because back in 1981, Voyager 2, one of the earlier missions of NASA, actually went close to Enceladus and unexpectedly spotted jets of something coming up from the satellite, the moon. So Cassini was sent to investigate this in more detail. And what it found was very exciting. The crust of Enceladus is basically solid ice, but shooting up from the surface are geysers. And these geysers turned out to be salt water with a number of minerals in the water. The spacecraft analyzed these. It had its trajectory altered so that it went through one of these geysers. And although it didn't have exactly the right analytical equipment, it showed that it was salt water mixed with various minerals and other potential organic components, which was very exciting because it indicated the possibility that there might be some very primitive life underneath the ice of Enceladus. These 4 images show, firstly, A is a cut through the moon of Enceladus and shows what we believe to be a very large ocean of water. The moon of Enceladus has a potential volcanic element due to its proximity to Saturn. The core of Enceladus, it's believed, sort of flexes, which causes it to heat up. These produce what is believed to be hydrothermal vents. The image on the top right shows what's believed to be underneath the crust of Enceladus, an ocean with hydrothermal vents. Now, this is particularly exciting because on Earth, we have hydrothermal vents at the bottom of our deep oceans. Image D, which you can see as a photo, you can see one of these or 2 of these hydrothermal vents, which are called smokers. Around those hydrothermal vents, unexpectedly was found a large amount of life. If you understand that the temperature in that area is several hundreds of degrees, it was unexpected. But nowadays, scientists believe that life on Earth possibly originated at the proximity to these hydrothermal vents. It is planned to go back to Enceladus to see whether or not there's any possibility of life under the crust. I've also added a couple of slides which might be of interest. The first one is various figures and information about the UK space industry. It was announced earlier this year that the government are investing a large amount of money into satellite communication. A lot of the small satellites, in fact, the UK is the biggest global producer of small satellites. It's an area of our expertise. There's quite a lot of companies in the UK that actually work on manufacturing satellites. Some of those are going to be involved in, hopefully, when man goes back to the moon. We happen to live very close to a very important place in the UK. Leicester is actually a centre of excellence for space exploration research. Leicester University in particular are world renowned for their involvement in space missions. I've given some examples of that, which I've taken from their information page. And I suggest that you go and have a look yourself at the Space Research Centre and also find out more about Leicester University. This year, the university announced, in collaboration with the government and a major player in satellite communication, and a space engineering apprenticeship scheme, which in conjunction with the University of Leicester will be offering places to potential students to do their university degree at Leicester University and their apprenticeship at a named company in the UK. It's very exciting at the moment in the world of space. You probably have heard of SpaceX, but there's also another company in the States called Blue Origin. Both of these companies, which are both owned by billionaires, in the case of SpaceX, Elon Musk, Blue Origin is Amazon's Jeff Bezos. They're both developing rockets and equipment which will help with the exploration of our solar system. It's planned that manned capsules made by SpaceX and potentially Blue Origin will be part of the project to go to the moon again and set up a colony, and also involved in the further exploration of Mars. NASA is carrying out a project called Artemis, which is involving those private companies and returning to the moon in the next decade and is hoped to set up a colony there. And finally, I'll come back to the first slide, and just to say that when I was your age and I was at school, it was part of the space race. I was fascinated with the Apollo program, and I watched the moon landing and stepping onto the moon the first time back in 1969. At that time, I really would have loved to have been an astronaut. But as things turned out, I had actually achieved part of my early dreams. As I mentioned earlier, I made and touched things which are in the Huygens lander, which is sat there at the moment on the surface of Titan. There's a question: what was it like working in the semiconductor industry, workload, etc.? It varied. In the early days, in the 70s, it was extremely exciting because we were creating a new industry. All of us were very young, all of the engineers, all of the operators, and it was a very exciting time. Didn't tend to think too much about the hours that we put in. Then later on, particularly in the noughties and 20s, we worked 8 hours a day, something like that. There was times when I've done shift work, but I must admit, I never sort of watched the clock, never thought about time as such. It was a case of working and doing exciting things. Oh, and I should say, it could be very dangerous as well. One had to be very safety conscious. The chemicals and gases are particularly dangerous. So health and safety was of paramount importance. A lot longer than you might think. For example, when I worked on producing the devices for the Cassini project, we actually worked on those for something like 4 years. Later on, when I was involved in developing the high technical devices in the teams, when I was working at Groovy, the devices ultimately took us probably nearly 10 years to do research, development, and get into manufacture. Some of those devices are the most advanced that can be found anywhere in the world for measuring pressure. So typically, projects could be anything from a year to 10 years. In actual manufacturing, to process a wafer from start to finish, in the part of industry I worked on, typically would take anywhere from 6 to 12 weeks. I would also like to say that if anyone at any time wants a presentation in person, I'm more than happy to do that, as the virtual type of presentation is a bit less interactive. So I hope you've enjoyed my talk, and I'm open to any questions.